Okay, I hope my voice is audible and my slides are visible to you. So this is going to be a summary session of this 12 weeks long course, which was Reagents and Organic Synthesis, conducted by NPTEL, whose course instructor is Professor Subhash Chandra Pan from IIT Guwahati. And I'm Deepika, your PMRF teaching assistant. I'm doing my PhD in chemistry at IIT Bombay. So in last 12 weeks, we have been conducting live sessions based on the video lectures provided in NPTEL channel on this course, Reagents in Organic Synthesis. So in this 1 hour long session, we are going to go through a few questions from last 12 weeks sessions, and it is basically a revision session. Okay, so I have picked a few very important examples from all these 12 sessions. So I hope it is going to be helpful for you. So let us start with the topic covered in week 1 of this course. So this is a question from the topic sharpless asymmetric epoxidation, which is widely used in organic synthesis because of its highly diastereoselectivity in giving the products. Okay, so if we revise the selectivity in this sharpless epoxidation reaction, you might remember that whenever we have an allylic olefin having an allylic alcohol of this type, we have to keep the visualization of the substrate in this way, and when we are keeping our CH2OH, which is allylic alcohol functionality, towards the right side down side, in that case, if we have plus diethyl tartarate or diisopropyl tartarate DIPT, if we have the plus isomer, that isomer is going to give us the epoxidation from the bottom phase, okay, which is the re phase. And if we have the minus isomer of either DET or DIPT, in that case we are going to get the epoxidation from the psi phase, which is the above phase. Okay, so if you have the substrate which is the olefin, if it is not in this fashion, if it is not placed in this fashion, suppose the substrate is given in this fashion, in that case you have to visualize your molecule in this way so that you do not get confused about which product you are going to get. Okay, for that you just have to simply rotate the substrate by 90 degree. Okay, because if you do not visualize the molecule in this way, you will not be able to write the correct product sometimes. Okay, so keeping this trick in mind, if we go back to our questions, we have this substrate. In the first substrate, if you see, we have two olefins. Okay, two double bonds are present, but the sharpless epoxidation will be observed only for that alkene which is containing an allylic alcohol substituent. Okay, so this first double bond is not going to react under this condition, and this allylic alcohol containing double bond is only going to give us the epoxide. So the question is, you are going to get the epoxidation from above phase or below phase. Since the plus isomer of diethyl tertiary is present, the epoxidation will take place from below the phase. Okay, so this epoxide we are going to get, and this reaction methodology is so effective that you get a very excellent enantiose selectivity in this reaction. Okay, and following the same reactivity of plus versus minus diethyl tertiary or DIPT, we can easily now tell which are the products that we are going to get in these questions. Okay, so in this case, if you see, in this case, now our alcohol is not present in the down right. Okay, it is present in the upright. So the selectivity will be reversed. And in this case, you can see that plus isomer is giving us the above product. Whereas in last question, it was giving the below product. And for question number 3, you just have to rotate the substrate by 180 degree. And since minus is given, the above the phase epoxidation will take place. And in fourth question, we do not have any allylic alcohol. We only have a carbon-carbon double bond. So mechanism-wise, it is not going to give us any product. Okay, so no reaction will be observed. And if you want to learn the detailed mechanism of sharpless epoxidation, it is given in the week 1 video lecture. Okay, Sir Pan has already extensively discussed the mechanism, how this allylic alcohol gets coordinated to the titanium center. In that mechanism, you will get all the details regarding this reaction. Okay, so moving to the next question, this is also from the topic oxidizing agents. Okay, and here we have TPAP oxidation of this alcohol, okay, which is labeled as red in color. So let us go through the mechanism that is involved in TPAP oxidation, which involves ruthenium metal. Okay, so it is also known as Ley-Griffith oxidation. So what happens here? It starts from attack of the alcohol that is present in the substrate at the ruthenium center. Okay, and the oxyanion of the ruthenium center will take up the alcoholic proton. So this is how we are going to get an intermediate product of this type, which leads us to the oxidation of this primary or secondary alcohol. Okay, and in TPAP oxidation, usually NMO, N-methyl morpholine, is also used, which can regenerate the ruthenium catalyst, as this ruthenium catalyst is highly expensive metallic oxidizing agent. So NMO is also used in the reaction for reactivation of the catalyst. Okay, so involving this mechanism, the alcohol functionality is getting oxidized into ketone. Okay, so Following the similar mechanism, we have only one alcoholic functionality in the substrate. So TPAB oxidation is going to give us this desired aldehyde. Okay, and in the note, it is written that only 12% yield is obtained by Swan oxidation. This is why in this for this particular substrate, TPAB oxidation is preferred over Swan oxidation. Okay. Then another question we are going to discuss from the topic oxidizing agents. Okay, this is a question from the topic Oppenheimer oxidation, and the reverse of the oxidation reaction is also known as Marvin-Pondor-Verley reduction. Okay, so let us go through the Oppenheimer oxidation mechanism, how this particular alcohol functionality is going to be oxidized into a ketone. So the mechanism starts with the alcohol attack at the aluminium center. Okay, this will attack and one of the acidoxy group will be eliminated. Isopropoxide group will be eliminated as the leaving group. Okay, so after the alcohol attack at aluminium, we are going to get this intermediate. Okay, now since alcohol is attacking here, that is electron donation is taking place from alcohol oxygen to aluminium, this oxygen atom is acquiring a positive charge. Okay, so this oxonium will be neutralized by deprotonation. Okay, so we get this isopropanol byproduct in the reaction. Then after deprotonation, we have this intermediate product where this particular fragment where you see R1 and R2 are coming from the alcohol attack. Okay. Now acetone comes into picture in the reaction. Okay, the reaction uses acetone also. So now acetone, which is present in a reaction condition, attacks again at the aluminium center, and in turn we get a kind of six-membered cyclic transition state. Okay, and this six-membered cyclic transition state at the end of the reaction can liberate the oxidized product, which is ketone. And how it is happening? This aluminium oxygen bond is breaking, and the electron movement will lead to the formation of carbon oxygen double bond here. Okay, and one proton from the alpha position of the alcohol is now transferred to the acetone. Okay, and this is how the secondary alcohol which was present in the reaction substrate is getting oxidized into this ketone. Okay, so open-air oxidation is widely used for oxidation of secondary alcohols. So for this particular alcohol, you see that even though we have epoxide also present in the substrate, the epoxide ring or this tertiary amine ring is not participating at all, and under open-air oxidation condition, only our alcohol is getting oxidized. Okay, it is just in place of acetone, we are using this cyclohexanone. Okay, but the mechanism will follow the exact same pathway. Then coming to the topic of reduction. Okay, and reduction using rhodium metal complexes we are going to see in this question. Imagine we are given only one equivalent of this rhodium metal complex, and if you look at the substrate, we have two double bonds. Okay, one is trans in fashion and the other is cis in fashion. So if we have only one equivalent of the rhodium complex, either this one or this trans one will get reduced. Okay, we will see how the selectivity comes when we have to carry out this reduction reaction. Okay, so the rates of hydrogenations decrease with increase in the alkyl group substitution on double bond, mirroring their relative binding affinities to the metal complex. Okay, So for this reduction, if you go through the mechanism in the video lecture, at first the double bond binds to this rhodium metal, okay. So the higher the affinity of binding of this double bond to the rhodium metal, higher will be their reduction, okay. And if we compare cis versus trans double bonds, the conjugation of cis double bonds will be relatively more feasible to the metal, because if we imagine the binding of the trans double bond, we will see that the binding will not be very good affinity, because suppose the metal is coming from this side, then this substituent will cause steric repulsion, okay. And if the metal is coming from this side, the cyclopentyl group will cause repulsion. So this is why the cis double bond is preferred, because the metal can easily approach from the face where there is no substituent, okay. This face will be preferred for metal conjugation and followed by hydrogenation, okay. So this relative affinity of binding in case of different olefins you can follow, okay. Then we have the same reagent, which is for hydrogenation. Again we have two different double bonds, okay. In this case both the double bonds are in cis fashion, so the binding affinity will come from the substituent present at the alpha position, okay. One double bond is containing a cyanide substituent adjacent to it, and the other double bond is not containing any such polar substituent, okay. So let us see what kind of selectivity is followed in case of this hydrogenation reaction when we have polar substituents present in the adjacent position of the double bond. So it is written that unsaturated substrates containing polar functionality are hydrogenated more rapidly. It may be due to easy coordination of olefin to the catalyst that is assisted by polar functional group. So if you see, again this reaction will be initiated by the metal binding to the olefin, okay. So the double bond which is containing the polar substituent is going to get bound to the metal more strongly, okay, and more rapidly. This is because of the electron pairs present in the cyanide substituent, okay. And thus if we have to choose any one of these two double bonds, you have to always first hydrogenate the double bond which is containing the cyanide substituent in the adjacent position. But if we are using excess of this hydrogenation reagent, in that case both these double bonds will be hydrogenated, okay. But if you have not mentioned any excess condition, that time you have to reduce only one double bond out of these two. Okay. Then let us move to this reaction from the Diebel age reaction conditions, okay. At first what is happening, we have a secondary alcohol present, okay, which is also containing an ester functionality, and this ester is alpha beta unsaturated. So in the first step of reaction we have TBDMS chloride in presence of imidazole. So TBDMS chloride reagent is used in organic synthesis for silyle protection of alcohol functionalities, okay. And we have already talked in the video lectures about TBS, TBDMS, TBDPS, etc. various silylating agents for selective oxygen protection, okay. So the first step is simple. In case of imidazole base, the proton abstraction will happen from the alcohol, and this oxyanion that will form is going to attack at the silicon center of the TBDMS group, and chloride will be knocked out. So this product we are going to get in the first step. Okay. Now we have this OTBDMS protected alcohol, and which is already present. Another functionality is alpha beta unsaturated ester. So we have 2.4 equivalent of diol H in the reaction condition. Let us see how diol H is going to react with this particular silide protected alcohol substrate. So for diol H reactions, at first what happens? Hydride transfer from the dipel molecule takes place to the carbonyl group. Okay, and after the hydride donation, the oxyanion that is going to form is going to do a coordinating bond with the aluminium. Okay, or you can show the reaction in this way. We have this aluminium center of dipel, and aluminium is containing vacant molecular orbital. So carbonyl group is going to attack at the aluminium center, and dipel is also containing a hydride. So this hydride will in turn be donated to the carbonyl center. Okay, thus we have this tetrahedral intermediate which is stable at very low temperature we can obtain. Okay, but if the temperature is raised above minus 70 degree, this intermediate is not stable and it can degrade. Okay, it can decompose. Okay, so after the formation of this tetrahedral intermediate, workup is carried out, and in the workup this oxygen aluminium bond is easily broken, and after breaking that bond, the ethoxide group is knocked out as ethanol. Okay, and we get the aldehyde formation for the reaction. So here we have an ester in the question. This ester will be oxidized, will be reduced to the primary alcohol functionality in presence of 2.4 equivalent of diol H. Okay, so this is the mechanism that it is going to follow. Then let us come to the topic, which is lithium reagents, particularly butyl lithium reaction. Okay, let us see how this alkyl iodide is going to react with tertiary butyl lithium, and the product will undergo protonation in presence of methanol at minus 78 degree Celsius. Okay, so at first what happens, the alkyl iodide will undergo lithium halogen exchange in presence of butyl lithium. Okay, and after lithium halogen exchange, we are going to get this alkyl lithium intermediate product in the reaction. And this alkyl lithium you can imagine to be C minus at this position, having the counter cation which is lithium plus. Okay, so since we have this protonating agent in the next step, this carbon ion will be readily protonated to give us this alkane. Okay, this alkyne. Okay, so this is how, using tertiary butyl lithium, we are going to convert this alkyl iodide into deiodinated alkyne product. Okay, then another very important topic, how we are going to convert this ester which is present, phosphonate ester, using Grignard reagent and aldehyde into an olefin. Okay, this reaction involves a mechanism which is quite similar to Wittig reaction conditions. Okay, let us see how this reaction takes place. At first, we have Grignard reagent, which also can act as a base. Okay, so in this particular question, we have a highly acidic proton present in this CH2 position of the substrate. Okay, so the Grignard reagent is going to abstract a proton from this position, and we get proton abstraction from this alpha position, and we get these resonating structure of the intermediate anion. Okay, and ultimately this anion, after abstraction of proton, reacts with the aldehyde present in the substrates. Okay, and this enolate is going to attack at the aldehyde, and we get another oxy anion by the electron pushing towards the carbon oxygen double bond. Okay, now this oxy anion is going to attack at the phosphorus center, which is present in the substrate, and we get a oxaphosphitane intermediate of this type. You may remember we also get similar type of intermediate in case of Wittig reaction conditions. Okay, and this four-membered oxaphosphitane is not very stable, so it immediately undergoes bond breaking in this fashion to give us the phosphonate ester along with the olefin, which is the desired product. Okay, so the ester group present in the first substrate is now coupled with the aldehyde, which is the second substrate, and the ultimate product that we are getting is the olefin. Okay, so this reaction is known as Horner-Wadsworth-Emmons reaction, and it is widely used in organic synthesis for these type of conversion. Now moving to the next topic, where we are going to see carbon-carbon bond cleavage using lead tetraacetate. Okay, you can see the net result of this reaction is this fused 5-membered cycles are broken into a larger ring. Okay, basically this carbon-carbon bond, which is containing the hydroxy substituents, is going to break to give us this 8-membered cycle along with the oxidation of the hydroxy groups. So this is the mechanism that is involved by lead tetraacetate reagent. Okay, it is well known for carbon-carbon bond cleavage of diols. So what happens at first, the lead center of lead tetraacetate is going to form a 5-membered ring intermediate by reaction with this diol. Okay, and how this happens we have already seen in the tutorial or video lecture. The one hydroxy will attack at the lead and one OAC will be knocked out. Similarly, again this alcohol can attack at the lead center. The second OAC can be knocked out. Okay, this is how we get the 5-membered intermediate of this type. And this 5-membered intermediate is not very stable, so it is immediately undergoing carbon-carbon bond cleavage by moving the reaction, the electrons towards this carbon-oxygen bond, and the carbon-carbon bond breaks to give us the second carbon-oxygen bond, and the lead acetate is removed as it is. Okay, so These two fragments of carbonyl compounds we get by the reaction of lead tetraacetate with diol. So let us move to the next question, which is again a very important reaction where the Barton ester is formed in situ, which can convert carboxylic acid into alkane. Okay, so the net result, if you see in the reaction, the elimination of a carbon dioxide molecule from the carboxylic acid is going to give us the alkane. So let us see how this reaction is happening. The DCC is given in the reaction condition, which is nothing but dicyclohexyl carbodiamide, and it is going to have a structure of this type. It is just in place of the isopropyl groups, we are going to have cyclohexyl substituents. Okay, and this rest is carbodiamide part will be same. And DMAP is used in the reaction. We are going to see how DMAP is also going to take place in the reaction. So the reaction starts with carboxylic acid, okay, and the dicyclohexyl carbodiamide is going to attack at the carboxylic acid for proton abstraction, and we get an the carboxylate of this type. And the carboxylate now is going to undergo attack at this electrophilic carbon center to give us this type of an ester fragment. Okay, and this ester now undergoes reaction with DMAP because the ester is having an electrophilic carbon center in this ester functionality. Okay, so DMAP will attack at this ester carbon, leading to this carbon oxygen bond cleavage. Okay, DMAP is attacking at this center, and this carbon oxygen bond is going to break to give us this second intermediate product, and the RCO part coming from the carboxylic acid now is joined to the DMAP molecule. Okay, now we have the alcohol substrate present in the reaction. So the alcohol is now going to attack at the ester functionality coming from the carboxylic acid. Okay, and the DMAP carbon nitrogen bond is going to break to give us this ester fragment. Okay, so this DCC coupling reaction mechanism is going to give us this Barton ester. Okay, like we saw, the RCO part from the carboxylic acid will link with this alcohol functionality to give us this Barton ester in the reaction. Now, this Barton ester is going to react with tributyl tin hydride in presence of AIBN. Let us see how this reaction takes place further. So, AIBN is nothing but radical initiator. Okay, so AIBN will break the tributyl tin hydride into hydride radical and tributyl tin radical, and the tributyl tin radical is going to react with the Barton ester in this fashion. Okay, this carbon sulfur double bond is going to cleave by homolytic cleavage to form this sulfur tin linkage, and the ester part will be removed by as this oxy radical. Okay, and radical in the oxygen center will again undergo again undergo carbon-carbon bond cleavage to liberate a carbon dioxide molecule, and the alkyl radical will stay. Okay, so now we have this alkyl radical liberated from the Barton ester, which is undergoing radical coupling with a hydrogen radical, which can come from the tributyl tin hydride. Okay, so since the AIBN can break the tributyl tin hydride into tributyl tin and hydride radical, so that hydride radical can couple with the alkyl radical to give us the desired alkane. Okay, so this Barton ester reaction can be used for conversion of carboxylic acids into alkanes. Moving to the next question, we have a diketone first, and these diketone are coupled into a carbon-carbon double bond using zinc and titanium fluoride. So this is a McMurray coupling reaction, which involves an electron transfer reaction from titanium to carbonyl group, and two such radicals which are arising because of electron donation from titanium can couple in this fashion to give us a 5-membered intermediate which can liberate the carbon-carbon double bond at the end. Okay, so in this substrate also, at first what will happen, the titanium will donate electron in both the carbonyl centers. Okay, and the oxygen ions are going to get bound to the titanium center in this way, and ultimately the 5-membered intermediate will break into this olefin. Okay, so this is how the McMurray coupling reaction is going to be followed. Then we have this carbon-carbon bond cleavage reaction using ruthenium tetraoxide. Okay, the mechanism starts with the electron donation from carbon-carbon double bond to ruthenium center, which will lead to the formation of this 5-membered ring intermediate by by ring formation of ruthenium center with the carbon-carbon double bond. Okay, and this 5-membered ring can either react with moisture to give us this diol as the product, and it can undergo carbon-carbon bond cleavage to give us this aldehyde and ketone. Okay, in one side we are going to get this ketone because we have a phenyl substituent also here, but in the other side we have only one proton at this carbon, so that is going to give us this aldehyde. Then we have question from oxymercuration demercuration part. Okay, let us see how carbon-carbon double bonds can be oxidized into alcohols in presence of mercury acetate. Okay, and in the second step, the workup is carried out in presence of sodium borohydride. So in oxymercuration demercuration, at first the mercury acetate reacts with the carbon-carbon double bond to give us a cyclic mercurinium ion. Okay, the electron donation from the carbon-carbon double bond can go to the mercury, and this mercurinium ion can be generated. This mercurinium ion can immediately get opened up in presence of moisture. Okay, nucleophilic attack on one of the carbons attached to mercury, resulting in the cleavage of carbon-mercury bond. So we get this oxonium ion by the attack of water molecule. Then deprotonation of the oxonium ion by the base acetate ion to give the alcohol from oxymercuration part takes place. So initially, if you remember, the acetate ion was liberated in the first step. So that acetate is going to deprotonate the oxonium that is forming. And we get this alcohol from oxymercuration. Now we have to carry out the demercuration step, and for that we are using sodium borohydride. Okay, so treatment with sodium borohydride replaces the acidoxymercury by a hydrogen atom, thereby creating a new carbon hydrogen bond. So this carbon mercury bond is broken by a hydride donation from the sodium borohydride, and we ultimately get this alcohol as our final product. Okay, so this is how in the reaction we have these two carbon-carbon double bonds, and at these two more substituted positions we are going to get introduced the hydroxy substituent. Now moving to the question from the topic hydroamination in presence of gold catalyst. Okay, so what happens, always remember, whenever we have gold catalyst or silver catalyst, activation of alkyne will happen first. Okay, so we have two different alkynes as substrates in the reaction. Let us see how the reaction is initiated. So the reaction starts from here. Okay, look at the second center, the compound number 2, which is this substrate. Okay, aniline. At first, this alkyne is going to be activated using gold catalyst. Okay, and simultaneously, the amine which is present in the aniline is going to react with an activated alkyne from the second substrate, and this reaction of this amine and the activated alkyne is going to give us this imine generation in the reaction. Okay, so this imine is now going to attack at the activated alkyne to give us intramolecular cyclization. And how this cyclization is happening? This imine will attack at the more stable carbocation that is forming. Okay, it cannot attack at this position, otherwise we will get a highly steric 4-membered ring. Okay, we get a 5 endo-dig cyclization, which is intramolecular cyclization by attack of the imine to the activated alkyne. So this is how we get this product, this indole product, starting from the substituted aniline. So another similar mechanism will be followed in this reaction, where we have this alkyne and a primary amine in presence of gold catalyst and zinc additive. Okay, and in this case we you can see that two different types of products are forming, where we have in the first product we have the R2 substituent on the nitrogen atom of pyrrole, and the pyrrole ring nitrogen is unsubstituted in the second product. So let us see how this mechanism is going to be followed. First of all, as we have a polar substituent present in the reaction, which is cyanide, the cyanide is going to be activated by the zinc additive present in the reaction condition. Okay, so the zinc is going to activate the carbon nitrogen triple bond, which will facilitate the attack of the amine at the cyanide carbon atom. Okay, and by the reaction of cyanide and primary amine, we get this enamine in the substrate. Now, this enamine can easily attack at the gold activated alkyne to give us intramolecular cyclization. So if you look at the enamine, we have two possibility of attacking the alkyne, either from this nitrogen atom or from this nitrogen atom of the enamine. Okay, so depending upon the attack of this amine versus this imine, we get these two different types of carbocations generated. Okay, and these two carbocations then undergo elimination reaction and aromatization reaction to give us two different pyrrole rings. Okay, so suppose this amine, which is NHR2, is attacking the alkyne. In that case, we have a substituent R2 at the nitrogen atom of pyrrole, which is the compound number 6. And if this imine is attacking the carbon-carbon triple bond, in that case, we are going to get no substituent in the nitrogen of the pyrrole ring. And we get the compound number 7 in this case. Okay, so this is how we are going to get a diverse set of products. Then we have this diol synthesis reaction, which was discussed in the week 11 tutorial. Okay, so we have this olefin carbon-carbon double bond first, and it is going to react with silver acetate in presence of iodine and acetic acid, which is a protic medium. So in this protic medium, we can see that the silver acetate and iodine is giving us cis diol. Okay, let us see how particularly cis diol is formed from this olefin under this condition. At first, iodination will happen for the carbon-carbon double bond, and we get an iodinium intermediate of this type. This iodinium is opened up by the acetate coming from silver acetate, and we get this carbon iodide bond breakage to get this acetate intermediate. Okay, now this acetate intermediate will undergo ring closing, where silver iodide is knocked out as the byproduct. We have now this 5-membered cyclic intermediate, which is protonated as we have protic source present in the reaction condition. So protonation of either of these two oxygen atoms will take place, which will be followed by ring opening reaction to give us this monoacylated diols. And at last, hydrolysis of this acylated substituent will take place, and we get diol as our final product. Okay, in this case, we have acetic acid present. So at the end of the reaction, when we have one hydroxy and one monoacylated hydroxy present, that monoacylated hydroxy group will be hydrolyzed by acetic acid. And in this case, in this way, we are going to get cis diols by this reaction condition. Now, let us see what if we have the same reaction condition present, silver acetate and iodine, but we do not have protic reaction condition, rather we have basic reaction condition present. Okay, so in case of basic reaction condition, where you can see we have potassium hydroxide, we will get a diol again, but it is not cis, rather it is trans diol. Okay, so this reaction is called Prevost modification of the earlier reaction, where after the formation of this 5-membered ring, there is no possibility of protonation present. Okay. In the last case, we saw either of these two oxygen atoms was getting protonated, but in this case, no protic source is present. So, another acetate will come from silver acetate and it will undergo SN2 reaction pathway to give us these two diacylated product but in trans fashion. Okay, so this is now hydrolyzed in presence of potassium hydroxide to get the trans diol as the final product. So you have to remember that protic medium is giving us cis diol, whereas basic medium or aprotic medium is giving us trans diol. Then we have this reaction from the topic Adams catalyst, where hydrogenation of this carbon-carbon double bond is taking place in presence of hydrogen and platinum oxide to give us higher amount of cis hydrogenation product. Okay, so hydrogenation reactions follow this kind of mechanism where the molecular hydrogen and the carbon-carbon double bond are first bound to the metal catalyst surface. In case of this condition, the platinum metal surface will bound to the carbon-carbon double bond and the molecular hydrogens. Then the hydrogen atoms from the molecular hydrogens are transferred to the alkene in this way, and after transfer of one single hydrogen atom, the second hydrogen atom is also taken up by the olefinic carbon-carbon double bond. Okay, and thus completely saturated alkane is produced after the syn addition of molecular hydrogen atom to the carbon-carbon double bond. So this similar mechanism is followed in case of Adams catalyst reagent. Then we have this cyclopropionation reaction in presence of samarium iodide and Grignard reagent, and the reaction will be finished by using TMS chloride at the second step to protect the alcohol which is going to be generated in the first step. Okay, so the reaction follows this pathway where at first the Grignard reagent will attack at the ester to knock out the ethoxide at ethoxide anion. Okay, so after the phenyl gets added to the ester carbonyl, the ethoxide will be knocked out. Then single electron transfer from the samarium center will take place at this ketone carbon. Okay? Then another electron from the samarium iodide molecule will be transferred to the substrate to cleave this carbon bromine bond. Okay? So we get a highly unstable diradical species in the course of the reaction. So this diradical that is formed will now undergo radical coupling to give us the cyclopropane, where the oxygen atom is coordinating to the samarium atom. And if we add TMS chloride to this reaction medium, in that case, the oxygen samarium coordination bond will break to give us the TMS protected alcohol, which is in 91% yield. Okay, and a similar kind of reactivity is also observed in this reaction, where this carbonyl group is going to react with the allyl functionality in presence of samarium iodide to give us the cyclopropane containing this alcohol functionality. So at first the single electron transfer will take place at the acyl chloride center, and that will undergo radical coupling reaction with this allylic double bond which is in a close proximity of the acyl chloride function. Okay. After the radical coupling, we have this carbon radical present, which will again take up a proton from samarium, and carbon ion will be generated at this carbon center. Now that carbon ion can attack at the carbonyl group to give us this cyclopropane ring formation. And at the end, acidic workup of this reaction is going to break the oxygen samarium bond, and we get the cyclopropane containing a hydroxy substituent as the final product. Okay, so these were the various questions which were picked from all the sessions discussing the 12-week long course Reagents in Organic Synthesis. Okay, so I hope you found this revision session helpful, and I hope you learned more or less various concepts based on this topic, reagents in organic synthesis. Okay,
Thank you, madam.
thank you so much for joining.
Thank you, madam. We'll see this week Friday. Saturday we have exam.
Can you please repeat?
Saturday we have exam, final exam.
Okay, is it in next Friday?
Next Saturday, next Saturday.
When is it? When is the exam?
Saturday, next Saturday,
Okay,
26th of this month.
okay. Please go through the video lecture questions, whatever were discussed, and I hope you have access to the slides that have been presented in the tutorials, right?
Yeah.
Yeah, you can also go through those slides, and the exam questions are not very difficult. Those will be conceptual only. If you know the concept of all the reagents, that will be very helpful for your exam. Okay,
Thank you, madam.
so all the very best for the exam, and you can solve the assignments provided for different week contents. Okay, those will also be helpful for the exam. Don't worry, the exam will not be very difficult. Okay,
Okay. Thank you, madam.
thank you so much. All the best once again for the exam.
Thank you, madam.